In a single week, 3 of the world's biggest AI labs accidentally allowed their models to break into real corporate systems. These breaches occurred during cybersecurity evaluations, the high-stakes tests designed specifically to prove the models were safely contained. This is a standard containment sandbox, intended to isolate a model from the live internet. However, a recent UK government report found that during these tests, AI agents took unsanctioned actions against 19 separate real-world targets. To probe worst-case behavior, testers intentionally disabled the model's internal safety filters. They meant to run the test in a sealed environment, but a human error left a path to the open internet, and the models simply traded real websites as practice targets. The gap between the model's power and the human configuration of the test box creates the immediate risk. A single misconfigured port turns a lab exercise into a live fire event. AI usage is shifting towards execution. Analysis of over 1 million conversations shows that 40% of prompts now ask models to produce a specific output or perform a task rather than just provide information. This satellite view of a cyclone represents the massive atmospheric datasets that Google DeepMind's WeatherNext now processes. The model matches the accuracy of traditional 2-day forecasts at a full 3-day lead time. To identify destructive outcomes, the system generates 1,000 distinct storm path scenarios in under a minute, a level of proactive calculation that provides coastal communities an extra 24 hours to evacuate. This autonomy is reaching software development through persistent async agents. Meta's new Muse code runs long-horizon coding jobs in the background, refactoring entire codebases without needing a human to supervise every step. As models evolve to operate independently over these longer periods, they begin to outpace the static environments we use to test them. The industry currently relies on a human overseer to manually approve an agent's actions before they execute on a network. A study of 40,000 approve or deny decisions shows a 33% failure rate. Overseers missed 1 in 3 genuine threats. As fatigue set in, the failure rate climbed. Reviewers began rubber stamping approvals, and 7% eventually approved every single prompt. Approvers waved through malicious commands 65% of the time when disguised as routine scripts, even when the logs showed the actual malicious code. Manual sign-off fails to scale with high-volume AI actions. When humans become the bottleneck, the primary safety net for autonomous agents effectively disappears. The benchmarks used to track AI safety are also showing cracks, often underestimating the actual capabilities of the models. Auditors recently found that a 60% performance ceiling on scientific coding was actually caused by broken test cases. Once the tests were fixed, model scores rose, revealing they were already more capable than the benchmark suggested. This capability is becoming proactive. New systems no longer wait for a bug report. They scout repositories and attempt to fix vulnerabilities entirely unprompted. With the failure rate of human oversight already at 33%, relying on a manual network sandbox to contain proactive agents creates a significant security gap. Safety layers are now moving out of the lab and into the software architecture itself. Mistral's Shieldstrol model is an example of this shift. It is a compact system that checks an agent's actions against safety rules at the exact moment of execution. This allows developers to define security parameters in plain English, creating an automated immune system that operates at the same speed as the agent. Managing autonomous agents requires moving past the limits of manual human review and building systems designed to monitor each other.